So today we're going to be doing this carnival ride problem. So it says, in a carnival ride, passengers stand with their backs against the wall on a cylindrical ride vehicle. So let's go ahead and draw a cylindrical ride vehicle, something like this. And we have a person up against the wall. And what we want to do is we want to go ahead and draw the forces acting on the person. So this cylinder is rotating about a central axis of symmetry. And let's say for the purposes of this example, it's rotating counterclockwise with an angular velocity of omega, let's say. So as the ride vehicle rotates, as we know, in the reference frame of the person, there's a fictitious force called the centrifugal force, which in this case will press the person against the surface of the cylinder, so we'll call that Fc. Now, in the actual formal free body diagram, we won't be drawing this force because it's not an actual force, it's just the body's inertia, okay? So we will also have, of course, the force of gravity acting on the person, which is mg, negative, and we also have the static friction force that prevents the person from sliding down. So if we were to actually draw a free body diagram, so here's the surface of the cylinder, here's the person, so there's a force of gravity acting on them, which we can calculate. The force of gravity would just be the weight, which, since they did not give us the mass, we'll just have to leave it as mg, okay? So that's just negative mg, negative because it's down. And then we also have the static friction force that is preventing the person from sliding down. Now, the person's back is pressing on the cylinder because the ride vehicle is rotating, so you do have this centrifugal force that is pressing the person against the wall of the cylinder. So therefore, due to Newton's third law, if the person presses on the cylinder will press back with an opposite and equal reaction force. So that is what we call the normal force, Fn. That's the normal force exerted on the passenger by the cylinder. So the center of rotation is here. So we will have an acceleration that is pointing towards the center. That is the centripetal acceleration, the rate at which we are changing direction. And so these are all of the forces that are actually acting here. Notice that I did not draw the fictitious force in this non-inertial reference frame, which is the centrifugal force, mainly because, of course, as you know, that's not a real force. So what we will do next is we will go ahead and sum forces. Well, we can, quickly draw a force table if you wish, with all of the components. So the Fn here, this one here, is actually an x component, so we'll go ahead and put it in the x column. The mg is a y force, so we'll go ahead and a y component, sorry, so we'll go ahead and put that in the y column. And then the static friction force is also a y component, so we'll go ahead and put that in the y column. So what we will do next is we'll go ahead and sum forces in the x direction, and we'll set that equal to the mass times the acceleration in the x direction. So when we sum forces in the x direction, what we want to do is we want to go ahead and add up all of the forces in the x column. So the only force in the x column is the normal force, so we'll go ahead and put that in there. And that's going to be the mass of the passenger. So that's m multiplied by the acceleration. And we do have an acceleration that is in the x direction. As you can see, the centripetal acceleration, since it's pointing towards the center, is actually pointing in the x direction. As you know, this is the x-axis, this is the y-axis, so that centripetal acceleration has only an x component and no y components. Now, as we know, the centripetal acceleration is v squared over r, so we have Fn is equal to m times v squared divided by r. Okay, so that's our first equation. Next, what we will do is we will go ahead and sum forces in the y direction. So let's go ahead and do that in red. So I'm going to sum forces in the y direction, and we're going to set that equal to mass times acceleration in y. So in the y column, I have this force here, these forces. So I'm going to go ahead and add those. So I have negative mg plus fs is equal to mass times v squared divided by r. Okay, so now I have this equation here. Oh, sorry. So actually the acceleration in the y direction is actually 0, mainly because the passenger is only accelerating in the x direction. The passenger is not accelerating up or down. So the static friction force is sort of preventing the person from falling, from accelerating downwards. So we have negative mg plus fs is equal to 0, so we have fs is equal to mg. Now, keep in mind that it asks for the minimum in the problem. So what is the minimum speed that the passengers can have so that they don't slide down or that they do not fall down? So in that case, we will be on the verge of sliding down. So this is really Fs max is equal to mg. Now we know what Fs max is. Fs max is mu s times the normal is equal to mg. Now, so we can actually substitute that normal force right in there. So we'll have mu s times mv squared divided by r is equal to mg. You can see here that the masses will cancel. And we will be left with, of course, mu s times v squared divided by r is equal to g. We can multiply both sides by r, so that will cancel here. So we're left with mu s here. Mu s times v squared is equal to g times r. And